To recap then, we have three basic material properties. There's the modulus elasticity, E, the Poisson ratio, nu, and the shear modulus, G. And you would think then that there must be three material properties that characterize an isotropic material, but it turns out that only two of these are independent. To show that takes a little bit more experience and background than we have time for. And so we're going to just write it out. It turns out that G is related to the elastic modulus divided by 2 times the quantity of 1 plus nu. So that is a very fundamental expression. It's a qualified memorize. So I'll put it like this. If you think you're going to have a career in solid mechanics and structures, it's a good one to have kind of locked into your brain. But it's not one that I would necessarily ask, for example, on an exam. But it is one that's very important. So again, getting to that point requires quite a bit of effort, which we're not going to take. But you can tell then, once again, that G and E have the same dimensions. So G, notice, is also going to be force per length squared. So 3 elastic properties, but only 2 of those are going to be independent for an isotropic material. One other little aside that we want to point out, and I'm going to call this again under pure shear. We wrote this out just a few minutes ago without elaborating on it. But whenever you have shear, you cannot simply have one value. If you have a value, say, of tau xy, then you also have to have a value along the top that's tau yx. And then along the back face, how we're representing shear, we have to have one going this way because it's going to be on the negative x face and the negative y. And then we have to have one going like this. So you can never just have one by itself. So we'll say that we do not have only one. We have 4. It is a quartet. Q-A-R. Quartet. There are going to be 4. And we say that heads, those are the heads of the arrows, and the tails, there are the tails, are together. And so whenever we think about pure shear, we think about there being 4 values, not just one. And that's something that we're going to keep repeating. It looks a little bit odd when you first see it. And it's a little bit like a uniaxial state of stress. If you have a normal stress here, you have to have one balancing an equilibrium there. And the same thing is true here. You have to have not only the forces being balanced, so this is this is this, but moment equilibrium about here. Notice that this creates a moment going this way. This one creates a moment going this way that's going to cancel. So whenever we characterize the state of stress, we always want to think then that there's going to be 4 values of shear stress as we write that down. Now, again, let's go ahead and summarize all of our symbols so far in this class. So our symbols. We have normal stress, we have shear stress. We have normal strain, we have shear strain. We have the elastic modulus or modulus elasticity, we have the Poisson ratio, and we have G. And my strong suggestion to you is you put these on a sticky note that has the name and the dimensions. And you take a look at that on a daily basis because you want those to really be so strongly embedded inside of your mind that you almost really don't have to think about that. That you can just think, okay, I know what those values are, I know what those symbols are going to be, and it's very simple to do. All right, let's take a look at a couple of examples then now that we've got these properties. And we're going to do a one that has the first two parameters, pardon me, and then a third that really weaves in a lot more. So this is going to be our axially loaded bar. So we've got a problem that looks like this. There we go. And so there is a loading here of P And there is a gauge length. In other words, there is a length right here that's originally going to be 4 inches. And then the length this way is 1.975 inches, like so. And the thickness, that's in this direction, that is T. T is equal to 0.375 inches. And then finally, we're applying a load of 6,000 pounds. All right, and what happens is there is a change in the length. So the delta in the 4-inch length, we observe this in the lab, it gets bigger by 0.023 inches. So it gets bigger, as we might guess. And then the change in the width direction, so that would be the 1.975. So the delta in the 1.975, because of the Poisson effect, gets smaller, 0.004 inches smaller. And the question becomes, find E and the Poisson ratio. So we want to find out what those two parameters are going to be. So really, we're just putting in numerical practice what we've already determined. All right, so the first thing that we want to do then is find the stress. So sigma is going to be equal to P divided by A. And when you're first learning how to do this, one of the challenges is to figure out, okay, which A? Which area am I looking at? Well, again, it's the one that's going to contain P. So that's going to be, that's going to be this one right here. So it is the cross-sectional area face that's perpendicular to the applied load. So that's going to be 6,000 pounds divided by 1.975 and the 0.375 inches. So we get 8101.3, and that's PSI. All right, so then we also can do the change in length over length. We can have the strain in the 4-inch direction. That's going to be plus, it's growing, so 0.023, all divided by 4 inches. And that's going to be 0.05750, and that is inch per inch. And so we can rewrite that. Remember, we would go 1, 2, 3, 4, 5, 6. So that would be 5750 microstrain. That's another way of looking at it. All right, so then the elastic modulus is just the stress over strain. So that's going to be, we don't even have to do those, we've got them right upstairs. So we divide that through and we get E is equal to 1,409,000 PSI, or we could say 1409 KSI. Either of those would be an acceptable unit to put on the modulus of elasticity. The Poisson ratio, we've got to be a little bit careful about that one. Remember, it's going to be the negative of the transverse strain divided by the axial strain. Now we haven't computed the transverse strain yet. So let's go ahead and do that embedded inside this calculation. So then we've got the negative sign. Then the transverse strain, it gets smaller, minus 0.004 divided by its original width, 1.975. And then we divide it by 5750 microstrain. So that's the axial strain, which we have already computed. And we find then that the Poisson ratio is 0.352. And again, that's a very common Poisson ratio for a structural material that we might see in a class like this. That example then is about as basic as we can get. It's one that you might see on the FE exam, so I'll say it is a classic FE type of problem. It would be a type of exam question that you might see. It would be just an introductory sort of question that you might see when somebody is trying to characterize these particular materials. Now, what about an example using shear? Let's take a look at that. Let me dash this out. So example, shear only. Now, this is actually one of my favorite problems. I'll just say a favorite. Because inside of this analysis is embedded a bunch of different behavior. So this will actually extend into our next part as well. So we're going to start with a sort of structural shape that's rigid, and it looks like a big U. I'm going to draw it like this. But it goes down to where this thing is basically flat. And so let me redraw the other side of this. And that is rigid. It cannot deform. So that's actually not the solid that we care about. So it is such a stiff material then that it doesn't deform at all. But along this side, we're going to adhere it to an elastic block. I guess I should say to an elastic block. And then the same thing over on this side. So it's going to be glued to these elastic blocks that are then fixed to a wall. So we've got a rigid, and then these guys are going to be elastic. And then we're going to put a load up here of 2,800 newtons on it. And the particular material properties then for this, we have to call out. But basically the deformation looks like this. As we push down on this, the only way that these two elastic blocks can deform is by shearing. They're going to move down like this, like so. So this thing shears down, shears down. So that is the style of deformation that's happening. So the reason that this is a nice problem is that it incorporates everything that we've learned so far. And we're going to pick that up then in our next and final part for today. But that concludes part C for today.